the title is Investigating the Behavior of Audio Classification Models Through Adversarial Attacks and Interpretability Methods. So this was done when I was at Queen Mary. My advisors are Emmanuel Benetos and Mark Sandler. So the title might seem a little bit long, but I'm going to break it down for you and kind of explain what I'd like you to take away from the presentation at the end of it. So the first part is investigating the behavior of audio classification models, just understanding how audio classification models behave, why they're good at their tasks, maybe why they're bad at their tasks, and how we can understand what features they rely on in order to perform these tasks as well as they do. And the kind of the techniques I'm using to understand these behaviors better is adversarial attacks and interpretability. And at first glance, these might seem maybe slightly unrelated, but I will explain why these two are related. So the overview of the presentation is kind of the first order derivative of deep learning models, which is kind of like the through line for the PhD and connects adversarial attacks and gradient-based interpretability, which is the type of interpretability that I'm focusing on. And with adversarial attacks, I'll just talk about how and why it is applied to audio and what are certain properties of adversarial attacks in audio. And with gradient interpretability, I will show some qualitative analysis of the results and also some quantitative analysis of the results. So let's start off with first order derivatives. So, this is this d of f of x by d of x. Most of us would have seen in our first calculus classes. And kind of what is beautiful about this function is that it is fundamental for training most deep learning models that we see today. And what makes it so useful is that it's quick to compute. It has a value of 0 at the local minima or maxima. And somehow, and through empirical evidence, we've seen that with some small modifications, it can train deep learning networks of almost any depth, complexity, and nonlinearity. And given that this first order derivative is able to do such a good job at learning features for the model, through my PhD, I wanted to explore maybe using these first order derivatives, what other information can we learn explicitly about how a model is making a decision. So the first way in which we're doing this is through adversarial attacks. An adversarial attack can simply be defined as a perturbation that's added to the input of a model in order to change the output of the model. It's usually used in a malicious context in order to fool the classifier into thinking it's some other label. So kind of if you look at the block diagram for this, there is basically you have a pre-trained deep learning model, which you don't, where the weights of the model are frozen. And then you have a target label. So the target label is basically the new label that you want the model to think the input is. And the only thing you're training is this perturbation array, which is going to be added to the raw audio of the signal. And kind of by doing this process iteratively and minimizing the loss function, as well as some sort of distance function between the original audio and this perturbation that you're adding, you can fool the classifier by adding a tiny imperceptible noise. And kind of why is this important for audio? Well, consider a case of a sound event classification system. And let's say your self-driving car is relying on the system to make decisions on the road. And now you have a fire engine that's coming and with a siren. And imagine that a malicious organization has made this or is either playing an ambient sound that's adversarial in nature or has directly modified the siren itself to produce an adversarial siren noise. And now your self-driving vehicle treats it as a benign sound, something like footsteps or a tire screech, and does not move out of the way. This could lead to accidents and undesirable behavior. So it's important that we understand how adversarial attacks can be used in this kind of, they present a security concern, and it's useful to understand why they're able to do this. And one of the key things in terms of this security concern of adversarial attacks in audio is the ability to transfer attacks from one model to another. Because you might think in the previous example, in the case of a self-driving car, that the average person is not going to have access to this deep learning model and therefore is not going to be able to directly target it and fool it. So isn't it not anymore? But with transferability, the idea is that you have a substitute model where you're kind of imitating what you expect the model you ultimately want to fool is, and you generate an attack on the substitute model, and then you verify with what accuracy it transfers over to your target model. And in our experiments, we mostly focus on the case where the training data was the same for the substitute model and target model. But otherwise, we experimented with different architectures for the target model and different input transformations as well for the target model. So the key findings from our adversarial attack work is that you only needed to add a small amount of noise, roughly around 60. The adversarial attack itself was 60 dB SNR, and to fool these audio classification models. And so basically, it was impossible to hear the difference between these original audio files and these adversarial attacks. So this kind of suggests that there is probably like this adversarial space that exists very close to the distribution of the training data that causes the model to behave very differently. So this probably means that the features that are learned by the model are not as are slightly kind of weak to these kind of perturbations. And maybe in cases like sound event classification, we want to be careful and ensure that the model is not susceptible to these kind of perturbations. With the transferability, we were able to show that if the input pipeline is the same, then 50% of the attacks which work on the substitute model also work on the target model. So for example, if the substitute model is a convolutional neural network and the target model is a convolutional recurrent neural network, and the input pipeline is identical. So by identical, I mean, it's a log-mul spectrogram, hop size is the same, window size is the same, everything is the same, then 50% of it transfers, even if there is significant difference in the gradients between a recurrent layer and a convolutional layer. Whereas if the input transformation is changed, so even if it's like, in the case that we experienced, the hop size was different between two different models and both had convolutional structures. We found that the transferability decreased all the way below 10%. And we also experimented with the case where we had a model that just took raw audio as the input. And then we tried transferring attacks from a log-mul spectrogram model to this raw audio model. Again, the transferability of attacks is much lower than 10%. So the fact that this input transformation is so important is sort of a unique problem to audio. It's not something you really see in image classification or natural language processing. And it kind of like shows, an important direction in which we need to use information from the audio community in order to understand this phenomenon better and maybe understand how, and we are also in the best position to understand how exactly these systems could harm models that we are trying to deploy in the public domain. So then moving on to kind of the next part of it is interpretability. So the structure for interpretability looks quite similar to the adversarial attacks, where basically the goal is that you're computing if you compute the gradient of the output with respect to the log-mul spectrogram, it could also be the raw audio, then that would be a saliency map. And if you compute the gradient of the loss function, of the output of the loss function with respect to the log-mul spectrogram or raw audio, that's called the loss gradient. And essentially what the saliency map and loss gradient do is they highlight sections of the input that are important for the model prediction. So both the saliency map and the loss gradient can have positive and negative values. And kind of the intuition that was there from previous work in image recognition, at least, was that the magnitude of the saliency maps are the most important, and a high magnitude shows that it's important for model prediction. And if it's closer to 0, then it's not as important for model prediction. So you're just kind of, and a lot of the analysis in existing work is usually qualitative. So we started off with doing qualitative analysis for music. So in this case, this is the task of singing voice detection. And immediately we kind of saw that it was not nearly as easy to identify any sort of patterns in the loss gradients for singing voice detection compared to kind of the things that people would see in previous work with saliency maps and loss gradients. One of the reasons is because log-MEL spectrograms are not very perceptible. Like for the most part, you know, if I gave you, even in this case, because it's the Gemendo data set, it's a fairly complex musical structure. So there's kind of a lot happening across the frequency range. But even if I gave you like isolated snippets of a single instrument note, for the most part, it would be very difficult to tell what instrument it is, what note it's playing, and things like that. So that is one issue. And then if you look at the loss gradient, there doesn't seem to be any clear correlation with the log-MEL spectrograms. Well, the only conclusion we could come from here is that the bright red spots and the dark blue spots, which indicate the strongly positive values and strongly negative values, respectively, they're kind of sparse in the loss gradients, which suggests that maybe there's just a small section of the input that's quite important for the model prediction. But before we go on to quantitative analysis, we wanted to try one more experiment where we aggregated the loss gradients. So essentially, the motivation behind this was that we were seeing that the extreme values for the loss gradients were quite sparse. So what if we just focused on the top 1% of the loss gradients and just kind of plotted the density of their locations across the test data set? And in this case, we ignored the sign of the input. So we just went based on previous assumptions that only the magnitude of the loss gradient is important and not the sign. And we plotted the kind of the location of the top 1% of inputs for the non-singing voice examples and top 1% for singing voice, and similarly the bottom 1% for non-singing voice and bottom 1% for singing voice. Let me start with the bottom 1% because that's, I think, quite easily explainable. So the bottom 1% would indicate that these are inputs where the gradient is close to 0. And we see that it's the density or the location of where these are across the data set is for the 80th Melvin, which suggests that at the highest frequency that we are considering. So this is a case of 27.5 hertz to 8 kilohertz. At 8 kilohertz, there's probably not enough information, or the model is not using that information very clearly to decide whether singing voice is present or not. And for the top 1%, we see that for singing voice is focused between the 10 and 20th Melvin, which roughly corresponds to 300 to 600 kilohertz, which is for, I guess, the typical singing voice where the first and second harmonics would be located. And for the non-singing voice case, it's kind of diffused across the entire log-MEL spectrogram, which suggests that there is no clear feature which defines what the absence of singing voice is. And another facet of these two is that they're focused around the 57th frame of the log-MEL spectrogram. And this, again, is what we'd expect, because the way the singing voice detection task is defined is that the ground truth label is annotated for the central 57th frame. So the fact that the model focuses on that area is ideally what we'd expect. But we still wanted to have some sort of a quantitative proof that this is actually highlighting features that are important to the model. So that's why we have this analysis. And with the quantitative analysis, the intuition is that we just select a different, so using the loss gradients, we use it as a mask for the log-mel spectrogram. And then we kind of replace the mask in this case with the data set minimum. And then we feed in these new masked inputs into the data. And then we compute the AURSC for this new masked test data set. And the goal is to observe whether there is still enough features present in order for the model to differentiate between the singing voice detection and non-singing voice detection. So if the interpretability method is bad, then you would expect that there would be a decrease, or if the interpretability method is bad and it's removing important features, or what I'm trying to say is, if let me just go to the next slide. So first, let me start off with the reference. So the baseline performance is the dotted line in blue that you see on top. And that is the performance on the normal test data set. And the AURC is around 0.96. And then as a reference, we have random occlusion. So this is where we randomly occlude different parts of the input and pass it to our model. So in that case, we see that there is a decrease in performance. It decreases to around 0.82. And at different, and basically we're occluding it at different percentages. So the interesting case is the case of RDOF GO, which is this kind of dark blue line on top. So gradient original is the original loss gradients that we plotted, which includes the sign of the input. And RDOF refers to removing in descending order first. So that means we're removing all the positive valued gradients. And what is interesting here is that the performance is actually better than the baseline. And similarly, in the case, if we take the opposite case, which is RAOF, which is removing an ascending order first, we see that the model performance is below 0.4, which for AURSC and a binary classification, that means that the model is performing worse than the random classifier, which means that a singing voice signal is consistently fooled as non-singing voice and vice versa. So essentially, it's the important finding is that qualitative analysis on its own is not as useful in music information retrieval tasks as it is in, let's say, image classification. And we need to complement it with quantitative analysis to actually verify if these interpretability methods are identifying sections of the input that are important for classification. And from, in the previous example, we saw that some features are, removing some features causes the model to perform better than the baseline, and removing some features causes the performance to drop worse than random classification. So that kind of behavior also has not been observed before. And it suggests that there's three types of input features to the model. So you have features that help the model make a correct prediction. You have features that help the model make an incorrect prediction. And then you have features that are not helpful for the model prediction. And it is, while those on its own is maybe that kind of intuition we might have had, it is good to know that they're strongly aligned with the loss gradients. And we can use that to kind of clearly separate these different types of input features. Another interesting thing is that in this case, we observe, so this extreme case all the way on the right refers to removing 98.91% of the features. We see that in the case of the RDOF for the raw gradient values, the performance is still above the baseline, which suggests that there is a lot of redundancy in the input features for the model prediction. And maybe this gives us an idea of the fact that, if we conduct these experiments for different stuff, different tasks, we'll be able to identify that we can maybe compress the features a little bit more, compress the models a bit more, and retain model performance, and help serve as a metric to design better models which are more suited to our task and what we're trying to achieve. That's my contact information if you have any additional questions. And these are the relevant publications. And that's pretty much it. Thank you.